Okay, I think we should get started. So welcome. Thank you for coming to this special informal astrophysics seminar. We're very pleased to have Reinhard Genzel from the MPE in Garking visiting today. He's a colleague, I think, who probably needs no introduction, but don't worry, I'm going to introduce him anyways. He's best known for his work on the kinematics of stars in the galactic center, which has given unequivocal proof for a supermassive black hole in the center of the Milky Way. This work is, I think, not just important, but really a fundamental step forward in our understanding of black holes and the dynamics of the galactic center. It's the sort of work that now appears in astronomy textbooks. And I myself have used the animations and movies that his group at MPE have produced of the stellar motions over the last few decades in both public talks I've given and also research talks. It's really astounding results that we've all appreciated. He's an expert on infrared and submillimeter instrumentation, and especially interferometry. He uses that to study the dynamics and structure of galaxies in their inner regions. He's, of course, had many accolades, but I would just mention the 2008 Shaw Prize, often called the Nobel Prize of the East, and of course the 2020 Nobel Prize, shared with Andrew Aguez and Roger Penrose, often called the Nobel Prize. He's visiting with Linda Tacconi, who will be giving a special Gallery seminar tomorrow at 11 a.m. in Peyton Hall, and I'd encourage everybody to attend that. Reinhard will be visiting Peyton tomorrow. So without further ado, Reinhard, please.
Thank you, Jim.
Tell us about the latest.
Well, I'm so pleased to be back. My God, memories come back for many visits in the past. Of course, some of you are not here anymore, but I can still feel them. So it's great to be back. Yeah, my subject is, it's a pretty normal subject, black holes. Everyone knows about black holes, right? What's new? Well, it's one thing to have indications of black holes. And another thing is to actually go ahead and measure space-time around these things and nail the actual physical meaning. And that's much, much harder, as you will see. Now, while I'm talking about experiments, I won't say much about experiments. I will just talk about the science, because there's so much science, and not just the science we are doing, but also other people are doing. Now, the key, very good. Already, first little glitch. Sometimes it gets stuck. That's good.
It's only at the start.
It's only
All right, it should work now.
Okay, thank you. So the three techniques which will be at the center of this talk, and it's not just the galactic center, is of course one which in the 19th century was invented by Michelson, interferometry. The interference of light in order to then measure the small shifts of the recombined light and thereby get very fine resolution, which in principle, as Charlie Towns would always say, it can be infinitely small if you measure extremely well. Now, infinitely small is a little oversaid, but still. So the one knows best, you know best, is radio interferometry, of course. That started first, is also, so to speak, the easiest of those, because of the long wavelength means that the accuracy you need in the equipment is still modest. More difficult, much more difficult, is to push the radio interferometry to very large baselines. And that has been attempted successfully over the last 30 years. Names like Jim Moran and Ken Kellerman and others come to mind, and have culminated in an experiment called the Event Horizon Telescope, which is telescopes all over the globe, and with baselines really truly measuring the entire diameter of the Earth, but now in addition also at 1 millimeter, which makes it difficult from the atmospheric kind of a thing. So the resolution of the EHT at 220 gigahertz is about 20 micro arc seconds, and that's the kind of a number to keep in mind, because that's about the event horizon size of a million solar mass black hole in the galactic center. So that's what you need, so to speak, this kind of resolution. Now, in the meantime, we have been able to do similar work, but now in the near infrared at 10 to the 4 times smaller wavelength. Now, that's something which previously only one person did, namely Albert Michelson. Michelson was the one who put on the telescope in California a device so that you could bring in light together from the outside of the telescope, bring it together and then focus it onto the mirror and look at stars and resolve stars. That was fantastic. It's just that after Michelson, nobody else got the experiment to work again for a long time. Charlie Towns did, but with a different technique, namely like in the radio, to mix down the wavelengths from the infrared into the radio bands. And that makes it, unfortunately, very insensitive because of so-called quantum noise in the infrared bands. Now, we have taken the same approach as the radio astronomers. Do it straight off. But that makes it really hard, but it works. It does work. And we have improved with this machine called Gravity, which combines the light from the 4 8-meter telescopes on Paranal Mountain by ESO in Chile, in resolution by about a factor of 15-20, and in sensitivity by about a factor of 10,000. We are working on another factor of 100 right now. So that breakthrough has made faint science interferometry possible. One application, the first one, was the galactic center, but then you will see in the talk later, we are now actually have gone the next step, and we are going to high redshift quasars. And that connects into another question, which many of you are very interested in, namely the evolution of black holes, which I want to touch on, and which has been brought to the forward of interest of many astronomers through the James Webb Telescope. Now, the third technique, of course, is in gravitational waves, and with the first wonderful results of LIGO and then the other Virgo Karga ground-based machines. I'll mention some of that, and in particular, at the very end, where I want to go and look at the future a little bit, the machine which I would like to do if I were young, and that's LISA. Space interferometry, which will allow you to do one key experiment which we all can dream of. Okay, so that's all I will say actually about the experiments, although the talk is entitled Experimental Work. So let's go and ask again, what about this black hole stuff? We know that black holes exist. If they're gamma rays or variable radio emission plasma jets coming out and so forth, that's very likely a very deep potential, which is a black hole. True, absolutely true. Don't dispute that. But experimental in that sense is something where you really make a measurement, which is you cannot refute. And that is, in the end, in my view, spatially resolved measurements of dynamics of test particles in the space-time. Test particles could be stars, could be gas, could be photons, and so that is what I will talk. Now, if you then think next, what if not black holes? Well, there is a whole plethora. If you look at the AstroPH every day, then you will find at least 5 or 6 papers of new ideas. The theoretical community, like you, many of you, are extremely inventive, extremely inventive. Now, obviously, you can characterize these other solutions by various parameters. One of them is the compactness. So if you measure through some means the mass of an object from a distant measurement, so that would be m in this equation, and then you able to measure the size, r, and then you construct this formula there, 1 minus 2 gm of r c squared, at least in spherical in spherical symmetry, then everything which has epsilon much greater than 0 is not a black hole. And the only thing which is a black hole is epsilon equal to 0. And there could be other things. There could be, for instance, concentrations of heavy fermions. And just like a neutron star, but with a heavier fermion, you could form fairly massive entities that way. That was proposed also a long time ago, actually. Likewise, bosons. You could think of that. That has also been proposed. Fell out of favor for a long time, but has come back very, very vigorously lately. And then there are other things, stars which are, basically held together by dark energy, gravitar stars, wormholes, da 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 da. On the wormhole business, since I'm a dumb experimentalist, I always refer to Roger Penrose. I say to Roger, they always ask me during public talks, what about wormholes? And then he said, rubbish. So don't ask me about wormholes because I will refer to Roger. Okay, so strictly speaking, what my job, what our job as experimentalists is to say, make measurements that constrain that epsilon there to be significantly less than 1, such there are no other solutions. And significantly less than 1, I would say, is significantly less than 0.01 to be really sure. Okay, so that's the job which we in principle have to do. Now, let's go a little bit into the history, of course. The first cases for such black holes only appeared about 60 years with the discovery of X-ray binaries, of which one of the stars was a hot X-ray source. And from the kinematics of the double system, you could conclude that this was, one of the stars was very heavy and not a normal star. So that's Riccardo Giacconi and others' work. The next one were the quasars, of course, and the discovery that there are objects at large distances which are extremely bright once you convert the apparent dimness into true luminosity, in the work by Donald Lindenbelt and Martin Rees, proposing that these objects which are accreting black holes of large mass could explain these quasars. And if these quasars are just sort of the tip of the iceberg, then maybe you could find them not only in distant quasars, but also nearby, including the galactic center. So the 1971 paper, in a way, was sort of a crossroads, because at that time, at least, it was impossible, not thinkable, to make measurements, dynamical measurements, as I told you, of test particles, to test the idea that the quasar has a massive black hole. We can do that now, but not at that time. And then finally, the galactic center. Now, the galactic center is very, very close by, of course, 27,000 light years. And as such, ideally suited, the radio astronomers discovered very early a compact radio source at its center, Sagittarius A star. Very, very compact indeed. We'll talk about that more later. But as you see from that picture there in the visible, very little else you can see in the optical. And that's because of our location in the plane of the Milky Way outside of the galactic center, looking into a very dusty region. And the dust is so strong, 30 magnitudes in the optical, that you cannot see the galactic center, even with the best telescopes. right in the very center. But in the infrared you can, in the radio also, at X-rays also. And so Charles Townes, when he moved from MIT to Berkeley and said, well, I'm going to do astronomy now instead of laser physics, and started a group doing infrared spectroscopy. And I became a member of this group, and one of our things we wanted to do is measure the motions of gas clouds near Sagittarius star. So there's Sagittarius star. The blue stuff are the stars in the center of the galaxy, and the pink and green are ionized and neutral gas clouds. And so indeed, over about a period of 10 years, we were able to measure at fairly coarse resolution, I should say, of a little less than a parsec, that the motions, and you see them down there in the Doppler shifts of these lines we are looking at, were great, hundreds of kilometers per second. Certainly not what you would have expected if there were only stars in the very center. So in Berkeley, anyhow, in 1985, we believed there's a black hole there. Charlie was convinced of that. There was no question. But nobody else was, of course, believed us, because they said, well, come on. Gas clouds you can push around with forces other than gravity. They make maybe magnetic fields and winds from stars. So that's not so good. And plus, honestly, the scales on which you have been making your measurements is effectively about 1 million times the event horizon size of a 1 million solar mass black hole. So there could be many other things in the center other than black holes. So chapter 1 ended, and chapter 2 starts, and then it goes on. I will not do this in this talk, to go through this sort of every 10 years and new instruments, higher resolution, going from gas to stars, and then from stellar motions to stellar orbits, and then even higher resolution to where we are now. Let me just basically state that in one step. Now we, of course, are using the biggest telescopes, just like the Keck telescope on Hawaii, where Andrea Ghez, Eric Beckley, Mark Morris, and others are working. We are using the ESO telescopes on Paranal Mountain, 8 meters, 10-meter telescopes, so very good resolution to look at the galactic center. There's one problem. Once you have an infrared imaging detector, which I should say was initially a real great hurdle, and you make an image of the center few arc seconds. So this is about a 3 arc second radius region in the center, centered on Sagittarius star, which is that red circle there. Well, you see, there is not much there in near infrared. But wait a second, we had a very famous Princeton astrophysicist who told us there should be a cusp of stars. Okay, there should be a cusp of stars here in the very center, and therefore a maximum of stellar emission and not a hole in the very center. So once that was found and no Bacall-Wolf cusp appeared on the images, Martin Rees left. He was a proponent of the black hole story in the galactic center initially, but then he said, no, okay, there's obviously nothing there. So what to do about it? Well, let's look a little more closely. It turned out there was one feature which Martin had overlooked, which is these stars which you do see are much, much more massive and much younger than the stars you could have seen if they would have wandered in on a relaxation time scale, which is in this case a few gigayears from the outside to the inside. So these stars, in fact, the big ones there, are a few million years old, so they cannot possibly have moved in through relaxation. In fact, we now believe, and I come back to this a little bit, not much, that they actually have formed another one of the things which shouldn't happen, so speaks against the black hole. You cannot have star formation from interstellar clouds near a black hole because of the tidal forces. Anyhow, so then we need higher resolution, obviously, and so going then from the CN limited resolution to adaptive optics, the picture changes. Wow, everything sort of gets smaller, a little hard to see. Let's amplify the image a little bit, and now you're beginning to see something is there near the red circle. Something is there near the red circle. It turns out that is what we now consider the strong evidence. These are relatively small stars, but very, very close to the center. And I'll tell you what we have found with those. So you can measure their motions. And when we did so, and then also the Keck group started doing this with the Keck, you find that they're moving at up to about 1,000 kilometers per second. And clearly, given the distances and so forth, that means 1 million solar masses on a scale of about 0.04 parsecs or 0.004 parsecs, something like this. So that's much better. Still not overwhelming, but much, much better. So that's how the story stood. And for the next 10 years, the two groups painstakingly measured these stars, ever better in signal noise ratio, but not in resolution. And so over time, we were able to see entire orbits. I'll show you that in a second. And from that, measure the mass and the distance to the galactic center. But then that is still not enough to really make sure that this is a black hole. So how do we get us to another factor of 20? Well, interferometry does do that. And so if you look at the central region right around the red circle with an instrument called gravity now, then what was there, all in the center now looks like this. There's Sagittarius star itself, a variable, faint but variable, highly polarized source, probably synchrotron emission, and various guests coming through, S24 and so forth. They change every year. They zip through there at very high velocities. And most of them initially were B stars. So again, doesn't make sense. I mean, they are young, maybe 50 million years old. How can they be, moving into the central region? Well, the answer is they're all, as you will see, on highly elliptical orbits. They're not in equilibrium in a Maxwellian distribution. And not all are B stars. There is this thing S38, you see that? Not bad. Well, that's a G star. That's very important because in spectroscopy, a B star just has very broad absorption lines due to helium and hydrogen. You can measure them well, but not extremely well. A G star has all these lines. So in the next generation with the ELTs, this is one of the key stars, because we'll be hopefully being able to measure then the velocities to about a few hundred meters per second or less, and then go to very high order in the post-Newtonian measurements. Anyhow, so summarizing all of this until a few years ago, we know of these stars in the innermost region on highly elliptical orbits. To the right there is the best one of them, which did its peri first in 2002. Both groups saw that all of a sudden, in March, it was on the right side, and then in October on the left side. Oops, something really has happened here. And you see that the distance at that point was about 15 light hours. So that's 3 times the orbital radius of the planet Neptune. And the motion was 7,300 kilometers per second. And the mass inside of that, again, the same mass, 4 million solar masses. And in fact, I should say, with the interferometry, which we were then able to do 16 years later when the thing came back and did its next peri, we were able to measure the motions from night to night. So that's the key thing to get to the accuracy we now have. So from this we have a mass accurate to about 0.2% statistical, 0.4% maybe 0.3% with all the other systematic errors, and likewise the distance. And the UCLA measurements are highly consistent with that. Now they don't have interferometry, so they cannot, in the end now, get as high a resolution, but the two measurements agree. And that's a very important thing in the Galactic Center, always was. One group makes a statement which is pretty outrageous, and another group says, nah, but here we agree, and even if we compete, we agree, and that's, of course, the scientific method as it should be. Okay, general relativity. So we can now go ahead and do the first orders of general relativity, ppn1. The strongest effect is the gravitational redshift. So when the star goes into the center, then of course, the lines from the star as they come to us are redshifted, depending how deep the star penetrates. In the case of S2, you see on the left side, if you subtract the equivalent Newtonian orbit, which is then horizontal, GR predicts the red curve, and the data clearly confirm that to 30 sigma accuracy. So that is okay. You can do things like the equivalence principle. So you test the orbital parameters estimated from a hydrogen line and a helium line. So according to GR, that shouldn't matter. You should get the same answer, and that's true. You do this nuisance parameter beta there does not depend on the properties of helium and hydrogen to not very high accuracy, but at least confirms the local positional invariance. The next big one is the precessions. So as you know, in GR, you have two precessions to worry about if there's no other perturber around. One precession is the Schwarzschild precession, which is prograde in the plane of the orbit. And in the case of the star S2, given its parameters, it's 12 arc minutes per orbit. So 12 arc minutes per 16 years. Then there's a second term, the lens steering precession, if the central object has spin. And that is, as you see in terms of the parameters there, R over A, the Schwarzschild radius, over A times 1 minus E squared to the 1/2 smaller. In the case of the galactic center, even with the maximum spin, that's a factor of 400. So currently, the lens steering precession with that star is not possible. We need a star which is closer, and I'll tell you, we have a candidate now. So if you do the same thing I did with the redshift, you subtract the Newtonian orbit, then in residual space X and Y, nothing happens. Okay, so that's that to say. So if you then put in the orbit we think the star goes through and switch on GR, that's what general relativity predicts for the Schwarzschild precession. You see the two Perrys in 2002, 2018, and we are now out there near, in fact, already the next Apo, which happens in 2 years from now. And the data with the interferometry is pretty close to what you would expect from GR, okay? So that is currently, depending on which data you intake, et cetera, sort of a 10 sigma type measurement. Now you would say, well, that's sort of nice, but others would say, but we know general relativity is true. No, don't we? I mean, why do you worry about all of this? Do we? Well, actually, there's another aspect here, and that is, suppose there were an extended mass, then we would get another precession, a retrograde precession due to Newton. And so by seeing the this FSP factor there to be so close to 1 means there is essentially no or little space for any extended mass. How little? Well, our measurement currently is within the upper distance of the star S2, about 2,000 solar masses. So that's, a very small fraction of the 4 million. And that's absolutely not expected. Certainly, remember, the coral wolf is supposed to be cusp. Where is that? Well, all the stars which should have meandered and came close to the center, there's only a few thousand solar masses of of objects, of which I should say the visible stars, which we observe, they make up, a few hundred. That's not the fact. They could be probably stellar black holes. By the way, if you put this measurement here, indeed, in the sense of a precession in orbit, then on the left side you see there's the earlier data from 2005 to 2008 in red, and then the new data in blue, and you can see indeed there is a sort of systematic shift to the right, which is 1/2 milliarc second. So that's the Schwarzschild precession of this orbit. Okay, so click, done that too. What's next? Well, we would like to go closer because the orbital peri approach of the best stars there is about 100 astronomical units, or equivalent of about 1,000 Schwarzschild radii. And again, you could have other configurations, like for instance that Fermi star, which I mentioned to you as a possible solution. So what can we do? We can use the infrared measurements and the millimeter measurements of a Sagittarius star itself. Now the worry is, okay, this is not stellar motion you're seeing. So now we're dealing again with gas physics. In the case of the infrared, you see the infrared emission from Sagittarius star is highly non-stationary. It's varying all the time on scales of hours, sometimes getting brighter by some factor of 10 to 30, then in others, 40% polarization. And in these active times, the infrared emission rises way above. In some cases, so way above that even there is a tail of X-ray emission seen. Okay, that's not always the case, but for the brightest flares, there's a effect due to X-ray emission, which nowadays actually is interpreted by most also as synchrotron emission, remarkably, not inverse Compton scattering. Okay, so there's a synchrotron source, and obviously very compact, very small, and varying. What could it be? And the proposal by Avi Loeb and others back in 2006 was, some hotspot. Magnetic reconnection brings up the energy higher. This is not an accretion event. This is not an accretion event. This is an event of energizing a few percent of the electrons in the innermost region to about somewhere between 1,000 and 1,000,000 times in gamma. And so hotspots. And so once you have a hotspot, you might expect, at least for the duration of its lifetime, before it gets disrupted, to see some kind of a motion. That was Avi's prediction, and others looked at that as well. And so that is true. So what you see there in this complicated diagram down there, on the left side, in X, in Y, and then in angle, is the polarization direction of the infrared emission. On the right side, X, Y, on the sky around 0, which is Sagittarius star, and again the angle. So if you put this in 2D, these are continuous motions clockwise in both directions with a similar, equal orbital time scale of 50 minutes, which is also one turn of the polarization. Okay? Now, this is not just one flare. This is an average of 6 flares over 6 years. They all do the same. And in the meantime, in fact, ALMA is beginning to see the same effect. Okay, so there's clearly a motion, and once you have that motion and you interpret it as a orbiting hotspot in a gravitational potential, then you can, of course, get some very interesting parameters, like, well, the orbital time is, I said already, about an hour. Then you find that the radius is about 9 Rg, or 4.5 Schwarzschild. It is interestingly face on. It's not like the Milky Way. Most people assume immediately if there's a black hole in the center, it ought to be parallel to the disk at large scales. Accretion onto a black hole is a local politics affair, and the local politics may be very different from the large-scale politics. So, yeah. By the way, that is confirmed, as you will see, by the EHT also. And when you then think that this is actually Keplerian motion, you get a mass of 4 million solar masses. Oops, that's the same as the prior from the stars. Now you could, of course, say, well, that's not accurate enough, and how do we know it's Keplerian? Maybe it's not actually expected to be Keplerian. There have been a number of people here, Elliott Quartet amongst them, writing about this. So it's still an interesting subject, but experimentally, it does fit Keplerian motion. It does fit, but now we are not anymore at 1,000 Schwarzschild radii, but at 4. Okay. Finally, the bending of light, which was, of course, expected since Bardeen and Luminet a long, long time ago, that if you have a black hole illuminated from the backside by some light source, then, of course, you get, like in Newtonian physics, the central part is blocked, but then actually the bending of the light extends much farther in radius. And in the case of a black hole, there is a shadow cast by the black hole, which is 5 times Rg. So the diameter of the shadow is about 10 Rg. 10 Rg. And outside of then could be a bright ring, because you have additional emission due to the accretion disk, etc. And that's what our EHT colleagues showed us 2 years ago, and the radius there is 50 microarc seconds. Now the prior, the mass and the distance from the stars lets you predict 51 microarc seconds. Okay, so not bad. So this looks like that size predicted. If it's that size, then we can also, of course, go ahead and get a mass, which again is 4 million solar masses, and we are again at about 5 Rg. Okay, let's summarize all of this. We now, over about 40 years, have been able to push, since Charlie Townsend's first measurements, inward. Then came the discovery of the stars and the orbits, which have been worked on by the UCLA and our group, with absolutely identical results. And now, finally, 2 measurements which are at least consistent with the same mass of 4.2 million solar masses. Now, there have been others, of course, who say, no, let's forget about this point here. It's not accurate enough. Could it be that basically that mass here is due to a fermion? And then you can, play with the Oppenheimer-Volkoff limit, what fermion mass you have. So from Ruffini's group measurements, so if you have a 40 kilo electron volt fermion, then you would expect the the Keplerian part to be here and then a break off here. Well, that obviously does not explain, however, the motions in the center. If you want to get at the motions in the center, well, then you need a mass of a fermion of 350 to 400 kilo electron volts, which is, largely disfavored by extragalactic measurements, and very, very close to, and suspiciously close to, gravitational collapse. So I would say for practical purposes in Occam's razor, that's not likely. So let me say, at least I would say that's pretty high probability that the sort of fermion ball and also the boson star possibilities can be excluded. Now let me, at the end of the galactic center part of the story, say something about the stars. The Bakor-Wolf. Yeah, okay, so if you plot the surface density of stars, there we are, surface density in log units as a function of distance, then the Bakor-Wolf of a single component mass distribution has a slope of r⁻⁷/4 in density, and so that's what this is. Now, if we look at the galactic center at the bright stars, they're down here. Okay, there's if anything, a hole. Likewise, the O stars, which are these yellow brownish things, they increase to the center and then there's a hole. Now let's go to the late type stars, which are the red ones here. And they're flat, and then there's a sort of a depression a little bit, but certainly flat. No Bakor-Wolf. Okay, so that's really the riddle. And at the same time, we see these stars, which we call the S stars. Initially, we thought they were all B stars, but I told you now we know there are also later types of those, the fainter ones. And they actually are very, very steep, steeper than the Bakor-Wolf cusp, but not many. So it's certainly not in the sense of the Bakor-Wolf. And so now we see, oh, this is much more complicated than we thought. A simple picture of what star clusters look like around black holes may be just not what we think it is. Because if you now go ahead and you measure for these blue stars the Parry distance in log units, here's Jupiter, Uranus, Pluto, etc., Kuiper belt, versus 1 minus e. So these are basically parabolic orbits. These are circular orbits. Then you see that the black circles, which are the S stars, form a sequence which obviously is highly elliptical, as S2. And there, look here, there is a star, which I show you later, which has a orbital radius of only a few times Jupiter. Okay? So they penetrate very, very deep at the cost of highly elliptical orbits. So they zip through there. Okay, so observing the galactic center with gravity 3 times a year is sort of like fireworks. They're all coming and going, and typically they're gone after 1 year, and then comes the next batch. Okay, so surely not a Maxwellian distribution of stars in equilibrium, which finally then fall and plunge into the center. So it's totally different. On the other hand, the massive stars, here the O stars, which are coeval, I told you, a few million years old, they are all out here on pretty low eccentricity orbits, and in fact in a thick plane, but certainly in a different structure. There's been an enormous amount of discussion theoretically. Is it possible that these stars, these S stars, have moved, have been scattered through various Kozai-Ledoff effects, et cetera, into the center, and some of them make it into these highly elliptical orbits? I would say the answer for that is probably not, because number one, the mass constraint, there is not a single O star which is amongst the S stars. Next, the central S stars are highly isotropic in terms of their angular momentum distribution. There is not a plane. This is to be seen. And the age distribution is much broader. I told you they're G stars. Okay, so the more likely situation is they're scattered through in there and then captured in a three-body process. That's called the Hills mechanism. Now, the details of how this happens could fill the next hour, but I don't want to do that. But I want to tell you that it's still a highly debated and highly interesting question. And it's so interesting because what we learn in the Galactic Center here, I would say, gives us a pretty good hint what you would expect in other galaxies which are not very active. Okay, so that's what we've learned about black holes and their environment in the local region. Now let's move out. We know that in AGNs, very bright AGNs, there's a central black hole, we think, surrounded by a highly radiative accretion disk, which you see in the ultraviolet or X-rays, surrounded by an ionized region of virialized clouds, we call that the broadline region, and then surrounded again by further gas, which you can see in molecules. And the broadline region, over many, many years, has been shown to follow a virial equilibrium. So if you measure the velocity width of the broadline region, and you measure the luminosity of the central region, which tells you something about accretion, then you have an equilibrium. The more massive the central region, the faster the motion of the broadline region. So we know these scaling relationships all the way up to redshift 6 or so. So that's where the James Webb, of course, is now hitting on. And you will find 3 papers a day of telling you that at redshift 10, we've seen very bright AGNs on the scaling relationship of masses of somewhere between 10 to the 6 to 10 to the 8 solar masses. That's a problem. And we will talk about that a little later. A better way, which is freer of assumptions, is indeed to measure it through dynamics. And this is what we've started with gravity also. For the first time on the famous 3C273 Martin Schmidt quasar, here is Paschen alpha. So that's the broadline gas. And you can see that relative to the phase of the continuum here, the blue side and the red side have different phases. So that means they're different positions. And if you measure through there, then you can see that this is basically a sequence which is going on a line with a direction which is perpendicular to the jet in this particular source. So the interpretation here is pretty simple, right? You have a rotating broadline region, and then the jet emerges from this region. So that works pretty well, and the mass which you get from this is consistent with the mass which we know from other measurements. But, and that's the next thing, is we know that, of course, this correlation between black hole mass and bulge mass stretches over many orders of magnitude, several orders of magnitude. And so in principle then, by measuring a black hole mass, we know what the galaxy mass is. And you know that the growth of the black holes, if it happens at Eddington, which is the fastest you can have, it doubles its mass every half a gigayear. So that means that, you know, it's possible to get a redshift 9, to get a 10 to the 9 solar mass black hole at redshift 5 or 4, but not at 10. That's not possible because you don't have enough time, even in Eddington limited accretion. So that's an obvious problem. Now, with gravity, we've been able to push now with a new technique we call gravity wide, where we're actually extracting the phases, bit like Michelson did. We're looking at a star which is away from the center and not in the interferometric beam, bring it in optically, correct for the phases, and then combine it with the central light. This is an experiment which people have tried for 20 years, has not worked. Frank Eisenhower was the inventor and builder of gravity, has within 2 weeks. Amazing. And so now we can measure basically phase reference to bright enough stars over about 30 arc seconds. And there are enough stars at that distance that we can reach redshift 2 quasars. And you see 3 of them down there. And you see, again, this pattern of the phases from one side to another. We currently have about 6 of them. And if you measure the masses in the horizontal scale, you see that this mass is significantly above the mass from the scaling relation. How much above? Well, okay, in one case, maybe it's a factor of 2. In another case, it's more like 10. So at least qualitatively, I would warn all James Webb enthusiasts, let's first go ahead and measure the masses at redshift 6 at least with the real method, and then be sure we can establish the black hole mass, galaxy mass relation at that redshift because of the accretion rates. If you convert this into accretion rates, the Eddington rate is by far not sufficient to build up these quasars. So we would conclude currently that to make these things, you better have super Eddington accretion. Now you can even make drastic mistakes. Here's one of them. Because of at very high redshift alignment, H alpha disappearing, people use other lines, like for instance carbon-4, which in this case is this yellow thing. Oops, the yellow thing, has a very, very wide and very, very blue shifted emission. So if you apply the scaling relationship to the yellow stuff, the mass comes out 20 times larger than with our data. So that's a problem. You have to have the right lines. So it's just a cautionary remark. Okay, let's see. I have no more time. Yeah, let me just briefly just sort of remind you of the LIGO results on the stellar black holes and what a triumph that was. Fantastic, fantastic experimental work, and how that goes on, and that the story here is the concern that there are too massive objects. Very few 10 solar mass times 2, 20 solar mass merged objects. Masses as large as 150 solar masses, where do they come from? In a single merger, that would not work because you have the pair instability gap. People are looking at the pair instability physics again to see how accurate that exclusion was. But other options, of course, is that you get mergers of super stellar black holes in dense regions at high redshift. Possibility. Or accretion, just like with supermassive black holes. And then came the favorite primordial black holes. I was at a conference, at least in Zoom this year. There was 1 week of primordial black holes. Okay, highly excited about primordial black holes. Let's see, so I wanna, you understand the first part was, of course, that at the Eddington accretion, you cannot explain even the redshift 2 quasars, and certainly not the redshift 6 to 10. I should say that the lensing, the micro lensing currently of the Milky Way by the Ogle group does exclude more massive halo black holes, which could be primordial black holes. So that means they can be very small, but then they wouldn't be of interest for the black hole question I'm talking about. So not clear whether the primordial, what to do with the primordial black holes at the present time. Okay, let me finish here. What do we do in the next years? Well, if I were young, I would say this star here is pretty nice. That's our newest star in the galactic center. There's Sag star. That's a tenth of an arc second there. Its properties are such that its pericentral approach is only 10 AU. Okay, and that is indeed in the corridor where lens steering position can be measured. The only thing from the data we have so far we don't really know is where the apo is. So we need to wait a little longer. If the apo, of course, is out there, well, then it will take a long time. But if you're lucky, and this thing has a 10-year type orbital scale, if it comes back, we measure lens steering. So that would be great. The next one is with the ELT. We are building currently the first flight instrument called Mikado. And with that, you can get very high resolution spectroscopy, like for instance on this G star, where you get sub-kilometer per second accuracy. And so if you do that, then you can get easily the lens steering and the quadrupole effect, and that gives you a test on no hair. With EHT, if you can go to higher frequency or still longer baselines, you can see the multiple orbits very sharply, which will give you a much improved measurement of the ring size. The combination of all those in the galactic center, EHT, these stars and the stars we know, may very well be a way to push deep enough on the beta parameter that we can exclude anything but a black hole. But the winner is LISA. Because if you have a situation of a stellar black hole merging into a supermassive black hole, then of course that takes several years and you have enough time to see in the in-spiral high signal noise ratios. And here are some simulations made which should get the delta epsilon, which here is called the delta Q, down to 10 to the minus 4. So that will be it. Then we can send one of you into the black hole. Thank you very much.
Any questions? Jenny.
I totally love this gravity redshift 2 stuff. I think it's incredible, but I wonder if you can talk a bit about remaining anxieties, like how much of the broadline region needs to be participating in this rotation component, how well we know R, and then also what range of parameter space you think you can get to.
Very good question. You saw perhaps that one of the 3 in the new ones which I showed, the pattern was that the continuum is not in the center of the shape. We see that for some of the local AGNs as well. There, it's the interpretation is that the continuum emission is not centered on the black hole. So that would be one. Another one would be outflow. And you are absolutely right. You know, it would be nice not to have to work with a few, but but to show you that we have now, you know, about 6 of those. Wow, what a difference. So let's all work on this. If you write a letter for me to the Director General of ESO that we all unfortunately have to take over for the entire VLT for the next.
Other questions?
Well, yes, on the S2 orbit again. So you have a constraint on extended mass from the lack of classical apsidal precession. Do you have any interest, given all the talk about Kozai-Ridolph and intermediate massive black holes outside the orbit of S2? Do you have an interesting constraint from the lack of change in eccentricity from one orbit to the next?
I'm getting scared. Yesterday, no, day before yesterday, I had a talk with a colleague in Berkeley who is working on this simulation-wise. And he tells me that, this is Wenbin Liu, and basically he tells me that their simulations indicate that on first approach, the binary will not be disrupted. So that the classical Hills mechanism doesn't work. But what will happen is it will harden the binary probably several times. And so there will be a sort of a post history of this entire story until finally you get a disruption. It shows you, however, how difficult, of course, in detail, these interactions may very well be. And so we don't know from where they come. We don't know how they get injected, and we don't know the details of the capture / ejection of the hypervelocity star. So that needs a little more work, I would say.
I can, I'll maybe ask the last question. When you talk a little bit about the flares, mentioned there were data was an average of 6 flares. Does that mean to say that the flares seem to occur at the same radius? All 6 of them were roughly at 9 RG.
Within the uncertainty.
So that suggests there's something very special in the gas physics there at 9 RG that makes it flare every time at that radius.
And note, I mean, the measurements from the variability of the millimeter emission is in agreement with this now. So it's not just us saying this, it's others as well. It's surprising. And why face on? Okay, let me say why it's face on. The galactic center, in my view, we always knew has a very low accretion rate. It's about 10 to minus 8, 9 solar masses per year. So that's a small fraction of Eddington. At that point, of course, Bodine-Peterson doesn't work. And that means that the angular momentum of the gas outside the event horizon, likely, if Elliot would be here, he should continue, but likely is the angular momentum of the original gas flow. Is there another angle we know like this? Yes, it's the massive star disk. So I think we're seeing the gas from the stellar winds from the dead captured, in the other galactic center, still flowing in.
Okay, thanks very much. Just thank you.